Now, one thing that you have to be able to do is to determine the magnetic flux through a rectangular area that is near a current carrying wire. And you may say, oh, that'll be easy. I'll just find the magnetic field, mu naught I over 2 pi r, and multiply it by this area of this rectangle, which is the width, w, times its height, h. The one thing you have to consider, though, is that as you get farther away from this wire, the magnetic field gets weaker. So I'm going to indicate that on here like so. The magnetic field close to the wire, and it's going to be going into the page here, is going to be very strong. I'm just going to show that by having these very close to each other. I've shown that by having those magnetic field indicators very close to each other. But farther from the wire, the field is weaker, as shown by this. Those magnetic field lines are farther apart, which shows that the field is weaker. These can just be considered as magnetic field lines going into the page. So the field gets weaker as you move that away. So we have to, instead of just multiplying one magnetic field times an area, we have to multiply an infinite number of magnetic field strengths times an infinite numbers of areas. So what we got to do is divide this up into a bunch of infinitesimal little areas like so. There's a little dA and a little dA right there and a little dA right there and a little dA right there, each an infinitesimal wide. So notice that because B at R equals mu naught I over 2 pi r, to get the magnetic flux, we're going to have to integrate B dotted on dA, where dA is equal to dr times what? Well, if this is dr wide right there, that's dr wide, what's the area of this little infinitesimally thin section? It's dr times h. H times dr. So all we got to do is integrate mu naught I over 2 pi r times the area h dr. And this is assuming that the area vector and the magnetic field are exactly parallel, which they should be. It's going directly into the page. And you have to integrate them from, it starts at r equals x, because it's this far away from the wire, x, and it ends up at r equals x plus w. So that'll get you started on that, and then you can figure out what the total flux through that little rectangular area is.